This is the last chapter in the fifth module. So, last classes we discussed about deflections of beams using Macaulay's method, simply supported cantilever, and how to find the maximum deflection. All those things we have discussed. So today we will take up the new chapter, columns. So all of you know that column is nothing but a vertical member. So suppose if you consider a building frame like this, these two are called as columns and this is called as beam. Horizontal member is called as beam. So this is, I have taken only column portion. This is the column. P is the load acting on the column. So if you draw a imaginary line passing through the CG of the column, that is called as axis of column. So that load P will be acting on the axis of the column. So this P is a compressive load. You can see that in all the problems of columns, so columns are subjected to compressive load, or it can be subjected to compressive load and also a moment, external moment like this. But we are dealing with only this case. What we are studying in this subject, they are subjected to compressive load. P is the compressive load here. So normally the load transfer in a structure will take place like this. So all of you know that roof is nothing but a slab. It is called as a slab. So normally load on the slab or the acted like over an area. So kilonewton per meter square is the area load which is acting on the. Then from the slabs the load will be transferred to beams. The beams are horizontal members. You can see that. So at some 3 meter, 4 meter intervals, these horizontal beams they are provided. So they will support the slabs. So beam loads are normally taken as UDL. Or in some cases, if some wall is coming on the beam, wall is resting on the beam, then the load can be taken as a concentrated load. Then the load will transfer to columns. Columns are nothing but the supports, which support. On the columns, the loads will be either can be of this kind. Then from the columns, the load will go to the foundation and then to the soil. So this is how the load transfer takes place in a structure. Detail in design. So in RCC design or steel design, in 5th semester, 6th semester, you are going to study about the design aspects. There you will be learning in detail about all this. Just I wanted to tell you that why I have explained this is columns, they normally transfer compressive loads. Compressive loads which are coming from the beams to the foundation or the footing, you can call. So that is the purpose of a column. In the case of a truss, you have analyzed trusses, method of joints or method of sections. Already, I think you are going to analyze. You have not studied that yet. So normally, in case of trusses, what happens? Forces will develop when the trusses are acted by forces like this at the joints. Like forces are these are the forces arrows what they have shown here. Some of the members they are subjected to tension force. Some of the members they are subjected to compression force. So in the case of trusses, if the force in a member is compression, that member is called as strut. So STRUT. So strut is nothing but a compression member. The word we are going to use in the case of truss. Whereas in the case of frames, building frames, we are called as columns. So columns are nothing but compressive load carrying members. Like that you have to define. Okay. So that is about the vertical member of a building frame or pillars of water tank, compression member of a truss which is called as strut. They are all called as columns. So the vertical member or compression member with sufficient length and relatively less lateral dimension is termed as a column. Meaning of that is length will be more. Normally the column length will be in the case of a building 3 meter, 4 meter, 5 meter like that. Whereas the less lateral dimension means it is a circular column diameter. So diameter is called as lateral dimension. So lateral dimension will be around 30 centimeters or 40 centimeters, 50 centimeters like that. Compared to the length, lateral dimension will be less. That is the meaning. If it is a rectangular column, then width and depth, they are the lateral dimensions. If it's a square column, width of that column will be the lateral dimension, like that. Okay. So you can have different shapes in columns also: circular, rectangular, square, then hexagonal columns. All those things will be there for architectural purpose. You can have different shapes in the columns. But anyway, in this chapter, we will study only about square, rectangular, and circular. Now, how columns are classified? So, classification. So, classification are based on the ratio of length to least lateral dimension. So, length to least lateral dimension. So, length is the, you know that this is length of the column divided by least lateral. This is the length of the column. If you take the cross section, if it is a circular or a square or a rectangular column, then its dimension is your lateral dimension. So, for example, if it is a circular column, diameter is the lateral dimension. If it is a square column, side is the lateral dimension. If it is a rectangular column, either width or depth. We call this as depth or thickness. You can call it as. So, width or thickness, they are the lateral dimensions. So if you take the ratio of length of the column to lateral dimension, least among these two, we have to take the least. Of course, in case of circular column, diameter is same in all the directions. Square also, both the sides are equal. But in the case of rectangle, one side will be more than the other side. So the least one among these two, you have to take the least, either B or D. In this figure, I have shown B as the least one. So B is the least lateral dimension here. So the ratio of L to that least lateral dimension. Normally we call it as D. D is the least lateral dimension. So in this case, of course, D becomes B here. So if you take the ratio, L is the length of the column, divided by D is the least lateral dimension, maybe diameter or width like that. If it is less than 8, then it is called a short column. It is called a short column. If it is more than 30, then it is called as long column. In between 8 and 30, if you have that value, it is called as medium column or intermediate column. You can call it as, you can write down that word. Medium column is also called as intermediate column. So depending on the ratio of length of the column to the least lateral dimension, which may be diameter or side or width like that. So you can classify the column into 3 groups here: short column, long column, medium or intermediate column. So that is one classification. Okay. Now I have some example here. You can see, suppose if the length is 3 meters and the diameter of the column is 500 mm, take the ratio L by D. So 3 meter should be taken as 3000 mm. So 3000 divided by 500, which is almost 6. So 6, which is less than 8. So the ratio is less than 8, L by D ratio. You can take it as a short column. I will take a square column. If you take a square column of size 300 mm, and if length is 3 meters only, then 3000 divided by 300, 10. It becomes 10. Ratio is 10. So it is greater than 8 but less than 30. So in between 8 and 30, this ratio will be there. So you can call it as medium or intermediate column. Next, if length is 3 meter, if it's a rectangular column of size 230 by 450, so one side is 230, another side is 450. So you have to take the least one. Least one is 230. So you have to take the ratio of 3000 divided by 230. So it comes to 13.04. Once again, it is greater than 8 and less than 30. It is a medium or intermediate column. Okay. So like that, you can have any examples you can have. Of course, L is equal to 5 meter. Circular column of let us say 300 mm, 300 mm or 250 mm diameter. Then you get 5000 divided by 250. So 5000 divided by 250 means it becomes 20. So it is an intermediate column. So like that, you can divide, you can classify the column based on the ratio of L by D. Now the next question is how the failure in column occur. So different types of columns, they fail in different way. For example, in short column, the failure of the column will be crushing. It is called as crushing. Failure will be by crushing. So suppose if you take this as a short column whose ratio L by D ratio is less than 8, if load P is applied here, so this column can take that load P to some extent. So when you go on increasing that load P, at certain value of P, that column will starts failing. So this is the type of failure that will take place in the case of short column, which is called as crushing. This type of failure is called as, so crack will develop like this. So this type of failure is called as crushing. So the failure will be by diagonal shear crack. This is called as diagonal shear crack. This is in the case of a short column. In the case of long column, the failure will be like this. See, the column buckles. So it is called as buckling or crippling. That is the word used. So when you apply the load P on a long column, let us take this as a long column where the ratio L by D is greater than 30. So then this long column will fail by buckling or crippling. So by increasing the load value P, at some value of P, it starts failing like this. So this type of failure is called as buckling or crippling. In the case, it bends like this, like a beam. Suppose if you take a beam, so when you apply load like this, so it will bend like this, So if you rotate this by 90-degree, this vertical member becomes a horizontal member and deflection will take place. In the last chapter, we have studied about the deflection. So here it is, in the case of columns, it buckles. We call it as buckling. There we call it as deflecting. That's all. So in the case of medium columns, whose ratio, L by D ratio between 8 and 30, then it may fail by either crushing or buckling. So either it can fail by crushing like this, as in the case of a short column, or it may fail by buckling as in the case of a long column. So it can happen in any of the ways. So short columns, they fail by crushing. Long columns, they fail by buckling or crippling. And medium columns, they fail either by crushing or by buckling. So this is about classification. Now there is very, very important definition called slenderness ratio. So please note down this. So plus slenderness ratio SR, I call it as SR. So different books, they use different notation. Some books they use lambda, some books they use some other notation like that. Anyway, I will call it as SR. SR means slenderness ratio. How do you define slenderness ratio in the case of a column? It is defined as the ratio of effective length of the column to its least radius of gyration. So here you should understand one thing called effective length. So L, you see this figure. In this figure, I have taken one end fixed, another end free, like a cantilever. The top end I have taken free, bottom end I have taken fixed for the column. Just like beam, you have boundary conditions here also. So a column is a vertical member, that's all. Beam is a horizontal member, column is a vertical member. So in this case, I have taken the bottom end as fixed, top end as free. So here L is the actual length of the column. Capital L is the actual length of the column. So you have one more called effective length, L effective. So L EFF, if I write L EFF, that is called as effective length of the column, which varies with the boundary conditions. So please keep that in mind, that the effective length of the column is different, actual length of the column is different. The actual length is L, effective length is L effective, like this. So this L effective value depends on the boundary conditions. So here fixed 3 I have taken. Sometimes both may be fixed, both ends may be fixed. Sometimes one end may be fixed, other hinge. Sometimes both the ends may be hinged. So there are 4 cases here. So all the 4 cases we are going to discuss in detail later. The boundary conditions, there are 4 types of boundary conditions. In this case, I have shown fixed and free, one condition. Second condition is both ends may be fixed. Third condition, both ends may be hinged. And fourth condition, one end fixed, another end hinged, like that. Okay. So that is the boundary conditions we are going to study in this chapter. So depending on the boundary condition, you have the value of L effective. So L effective depends on the boundary conditions. Keep this in mind. So that we will discuss in detail later. So L effective divided by least radius of gyration. So what do you mean by radius of gyration? You have studied this in your moment of inertia in engineering mechanics. Radius of gyration is denoted by K here. So K is equal to square root of I by A. I by A. So I is the moment of inertia, divided by A is the area of that section. Okay. So moment of inertia of that column section is called as I. A is the area of the column, cross-sectional area of the column. So if you calculate K root of I by A, L effective divided by K is known as your slenderness ratio. But here we take K minimum. So this you should understand. So here what happens whenever you are calculating moment of inertia, you are calculating moment of inertia about any of the axis. For example, in the case of circular section, circular column, your moment of inertia is same in all the directions. That means about x-axis or y-axis, moment of inertia remains same because diameter is same in both the directions. In the case of square column also, you have the moment of inertia BDQ by 12. Whereas in the case of rectangular column, moment of inertia will be different because B and D, they are different, you know. So IXX. So if you take horizontal axis, centroidal axis as XX axis, in the case of rectangular column, it is BDQ by 12. IXX will be BDQ by 12. Whereas IYY will be, if you take about the vertical axis, its value will be DB cube by 12. DB cube by 12. So these things you have already studied in your mechanics about the moment of inertia, and I explained about moment of inertia in the bending stress chapter also. Very important concept. So BD cube by 12 or DB cube by 12. So among those two, whichever is lesser, that we have to take there. That is the meaning. So if you want K minimum, you have to take I minimum. I minimum is you have to calculate both IXX and IYY about both the horizontal. You have to locate the centroid of that circle or rectangle or square, whatever it is, and whatever axis is passing through that centroid, that is taken as horizontal axis is taken as x-axis, vertical axis is taken as y-axis. So IXX is BDQ. That is in the case of a circular section, you know that moment of inertia is pi d power 4 by 64. Pi d power 4 by 64. All this you should remember. So we have used it already in bending stress chapter also. Pi d power 4 by 64 is the value of moment of inertia. IXX is equal to IYY is equal to pi d power 4 by 64 in circular section. You can make a note of that. Then in the case of square section, if I take both the sides as B and B, so then there also IXX and IYY will be equal. Square section. IXX is equal to IYY is equal to B into B cube by 12. Okay. Same as rectangle, but B is equal to D. That's all. So that means B power 4 by 12. So in that case also, both are equal in square section. Then coming to rectangular section, IXX will be BD cube by 12. If you take the width as B, depth as D for a rectangular section, so BD cube by 12 is IXX, DB cube by 12 is IYY. So please make a note of that. So you have to calculate both of them, and out of that, whichever is minimum, that is taken as I minimum, and square root of I minimum divided by A is called as the minimum radius of gyration. So I have done it. See here. Next, here I have shown that. See here. In the case of rectangular section, you see I have taken this as B, this as D. IXX is BD cube by 12. IYY is DB cube by 12. Interchange B and D, that's all. So in this case, you can see IYY is less than IXX because, see, if you observe this here, B is less than D, you know. So B is less than D or D is greater than B. Since D is greater than B, naturally this is more. This is more than this. So therefore, this is minimum. So IYY is minimum, is less than IXX. Therefore, when you are calculating K minimum, that means your minimum radius of gyration, you have to take the minimum of IXX and IYY. In this case, it is IYY is minimum here. So therefore, square root of IYY by A. So IYY is B cube D by 12. Divided by what is the area of this section? B into D. So if you simplify this, you will be getting B divided by 2 root 3. So this is the minimum radius of gyration in the case of a rectangular section. Okay. In the case of a square section, what happens? As I already told, IXX is equal to IYY here because sides are same. B is equal to D. So BD cube by 12. In that case, B is equal to D. Or 4 by 12 you are going to get. So since both are equal here, your K minimum will be, you can take any one of them, either IXX or IYY. So B power 4 by 12 divided by area is B into B, that is B square. If you simplify this, you by 2 root 3. Here also you will get b by 2 root 3. Here also you will get b by 2 root 3. So even though the sections are different, square and rectangle, your minimum radius of gyration remains same, b by 2 root 3, b by 2 root 3. Now in the case of a circular section, diameter is d. I have taken diameter as d. Here also ixx and iyy, they are equal here because of same diameter in both the directions. So pi d power 4 by 60. That is the formula for moment of inertia of circular section about the centroidal axis. Now k minimum is now root of ixx by a. Anyone you can take. Both are equal. So if you substitute and simplify, here a is pi d square by 4. If d is the diameter, capital D. So this is capital D. If d is the diameter, and if you simplify that, you will get k minimum as d by 4. So this is how we can calculate the formula value of k minimum. You need not remember the formula, but I value and area value you should be knowing. That's so you will be having two values of I, one about x-axis axis, another about y-y axis. So among those two, whichever is minimum, that value of I we have to take to calculate the minimum radius of gyration. Whereas in the case of circular and square, they are equal. So you can take that value, ixx or iy. So the thing is, the column buckles about the axis which has least radius of gyration. That means the failure of a column takes place about the weaker axis. So weaker axis means, suppose if kyy is minimum, kyy is minimum, then yy axis is the weaker axis. It buckles about that axis. Suppose if kxx is minimum, it buckles about that axis. It fails about that axis. That is the minimum. So this is about the first classification, and I explained about slenderness ratio. So slenderness ratio is the ratio of effective length of the column to the minimum radius of gyration. So minimum radius of gyration is given by square root of minimum moment of inertia divided by cross-sectional area. So minimum moment of inertia is the minimum of ixx or iyy. So this is how we have to calculate the slenderness ratio. Now, based on the slenderness ratio of a column, columns can be classified as, see here, this is another classification. So first we discussed about the ratio of L by D. Yeah, L is the actual length of the column to minimum least lateral dimension of the column. So if you take that ratio, then columns are classified as short, medium and long based on the values L by D less than 8, between 8 and 30 and more than 30. Whereas if you classify the columns based on slenderness ratio just now I defined, it's the ratio of effective length of the column to minimum radius of gyration. If you calculate that value, slenderness ratio value, and if that value is less than 32, less than or equal to 32, then the column is called as short column. If that value lies between 32 and 120, it is called as medium or intermediate column. If that value lies, it is more than or equal to 120, then it is called as long column. So you have to note these numbers: 32, 120, in between 32 and 120. So slenderness ratio. So based on slenderness ratio, columns are classified, and based on L by D ratio also columns are classified. So short, medium or intermediate and long columns. Okay. The thing is, short columns, they fail by crushing. Long columns, they fail by buckling or crippling. Both are same. And the medium columns, they fail either by crushing or by buckling or crippling. Okay. Yes. Next definition is crushing strength of column. So this is next definition. So these are all the definitions. Before going to the derivation and problems, we have to understand these definitions. So this, as I already told, this crushing will take place in the case of short columns. In the case of long columns, it is called as buckling or crippling. So crushing. So it is the load taken by a short column at which crushing occurs. That means it is the maximum load. We can add that word. It is the maximum load a short column can take before crushing. Like that you can write. You can write like that also. It is the maximum load that a short column can take before crushing occurs. Can take. So that value is called as PC. So C stands for crushing. acting exactly along the axis of the column. Please note that. So I have taken the load along the axis of the column, and it is a compressive load. Columns always take compressive load. There is no question of tensile load, but it can take moment. But in your syllabus, you are studying only about axially loaded columns. Axially loaded columns means the compressive load is acting exactly along the axis of the column. It is not acting here or here. It will be acting here only exactly. Okay. Now, how to get that crushing strength or load, crushing load of the column? So we know that stress is equal to load divided by area, or the resistance divided by area. Here that means then in that case load is equal to stress into area. You are going to get stress into area. So this PC is can be written as FC into A, where FC is the crushing stress, which is expressed in Newton per mm square, and A is the cross sectional area of the column depending on the shape of the column. So over which this load is acting. If it is square, it is pi d square by 4. If it is rectangle, it is B into D, like that. So area, cross-section area of the column, normally it is expressed in millimeter square. So stress in Newton per mm square multiplied by area in millimeter square, you are going to get the load in newtons. Then you can convert it into kilonewton. Normally loads are expressed in kilonewtons. So for one kilonewton is 1000 newton, that you know. Okay. So this is how the crushing load is computed. Stress, crushing stress multiplied by the cross-sectional area gives the strength of the column. Okay. Then buckling load. So buckling load or crippling load, it is denoted by PCR. CR means crippling. PC means crushing. PCR means crippling. So I am using the same notation throughout this chapter. So in the case of, see here, what you can say, it is the minimum load at which a column tends to buckle. Okay. It is the minimum load at which a column tends to buckle. That means when you go on increasing the load of the column on a long column, please note that it is on a long column. So always long columns, they fail by buckling or crushing. That is the word you have to use. Crushing for short column, buckling or crippling for long column. So it bends like this, column bends like this. Whereas in the case of crushing, diagonal shear crack will develop. Whereas here, the entire column will bend like this. Depending on the boundary condition, you can draw that bending curve. Okay, like just like your beam you have done in deflection chapter, you know. So it is the minimum load at column tends to buckle. That means when you go on increasing that load PCR, this is actually PCR. When you go on increasing that load acting on the column, some value of the load, it tends to buckle like this. It tends to bend like this. Column will bend like this. So that load is called as, at which it starts bending, it is called, or buckling, it is called as crippling load. In the case of columns, we call it as buckling or crippling. In the case of beam, we call it as bending. Okay, that's all, bending. In case of beam, it is called as bending. In the case of column, it is called as buckling or crippling. So it is the minimum load at which a long column tends to buckle, starts buckling. A long column buckles about an axis, once again, which has least moment of inertia and least radius of gyration. Naturally, if Ixx is minimum, it buckles about that axis. If Iyy is minimum, it buckles about that axis. It is computed by applying Euler's formula. So this is one important formula which we have to derive. Formula for columns. That will derive later. Its value depends on the type of end conditions. That is very important. End conditions of the column. End condition means support condition. Fixed, hinged, free. So I told you, 4 cases. Here also I have shown one end fixed, another end free. So if it can be both ends fixed, it can be both ends hinged, or it can be one end hinged and one end fixed, like that. So depending on that, your value of buckling load or crippling load will vary. So length of the effective length of the column also varies with the end condition. Crippling load also varies with the end condition or support condition. Now let us see what are the end conditions. So as I already told, so we should understand about the characteristic of those boundary condition. End means boundary condition. Suppose if it is a fixed end. If it is a fixed end, I have explained this in beams also in the deflection chapter. So in the case of beams, if it is a fixed end, both slope and deflections are zeros. In the case of cantilever beam, at the fixed end, slope also zero, theta is also zero, deflection is also zero. So similarly here there is no slope, no deflection, no slope at the fixed end. In the case of column, it is shown like this. This is the fixed end. This is the free end. There is no support here. So in this case, how it buckles? So suppose if you turn this by 90 degree, it becomes a cantilever beam, and this P will be acting. This also P also should have to take like this here at the free end. Then it this deflection will be different. So here also at the fixed end, as we know at the fixed end, this is the fixed end. Please note that I am only applying here. Here slope is zero, deflection is zero. Both are zero. So slope means dy by dx. Only thing is here x is measured like this. X is vertical here, y is horizontal. Because it's a vertical member, along the length of the member x is measured, perpendicular to that y is measured. It is opposite of beam. Okay, beam is horizontal, column is vertical. That's all. Now here at this fixed end A, deflection is zero. That means there is no deflection here. This point won't move. Whereas slope is also zero. That means dy by dx is also zero. That means here, if you draw the curve, this is called as the buckling curve. So there it is called as deflected curve or elastic curve. In the case of beams, here it is called as buckling curve. So this buckling curve will be like this. This is also an elastic curve. Okay, elastic curve means if you remove this load, it will come back to its initial shape. That is the meaning of elastic. I have explained that in the first chapter itself. Elasticity, plasticity, all those things. So this A at the fixed end A, slope is zero, deflection is zero means there will not be any rotation here. Okay, so it will take a shape like this, and this side, depending on the condition, it will buckle. Okay, don't worry about that. So fixed end, it will be like this. This is the meaning. Deflection zero, y zero. Y means y is measured like this. X is measured like this. Rotation zero or slope zero means theta will be zero. Dy by dx will be zero. It is also called as restrained against direction and position. So some books they use this word. Fixed end means restrained against direction and position. Direction means y. Position means dy by dx. Please note down that wording. In some books they use that also. Next, second is hinged end. So we know that at the hinged end, deflection will be zero, but rotation will be there. So theta not equal to zero, or dy by dx not equal to zero. Suppose if A is a hinged end or a pinned end, you can call it as a pin also. Pin and hinge, they are same. Theta is not zero, but y will be zero. So dy by dx not zero, but y will be zero. That is the condition. So in this case, it is restrained against only direction. That means there is no deflection, Therefore, it is restrained against direction, but it is free against position. So it can rotate, but it cannot translate. We call it as translation. Translation means deflection. These are the words, technical words. So then free end. So third condition is free end. See, this is the free end. In this free end, what happens? Just like cantilever beam, it has both rotation as well as deflection. So y not equal to zero, dy by dx not equal to zero. So this is opposite of fixed end. In fixed end, both will be zero. There is no deflection, there is no rotation or slope. Whereas in the case of free end, so both will be there. They will not be zero. So it will deflect like this. If you turn this column by 90 degree, it will look like a cantilever beam. Okay, so this is at the fixed end it is zero. At the free end you have some rotation as well as deflection. So these are the characteristics of support conditions in the case of columns. Similar to beams, there is no change. So in this case we call it as it is not restrained against direction and position. So that means it is easy to rotate, it is easy to deflect. That is the meaning. It is not restrained, not restrained. Restrained means fixed. That is the meaning. Now we will come to stability of column. What do you mean by stability of column? There are three cases: stable, unstable, and neutral. Neutral equilibrium. So stable equilibrium means Suppose if the whatever load is acting on the column, if that P is the actual load acting on the column, PCR is the crippling load of the column. That means crippling load means it is the minimum load at which a column starts buckling. That is or crippling. It's called crippling load. If that actual load is less than crippling load, then it is stable. That means it is strong. It won't fail. That is the meaning. So PCR means it is a nothing but the strength of the column. It gives a value of strength of the column. Whereas this P is the load acting on the column. If the load acting on the column is less than strength of the column, definitely it won't fail. Unstable means if the load acting on the column increases, then is more than the strength of the column, naturally it fails. It buckles like this. See, it buckles. Here there is no buckling, but here it buckles. Buckles means it started failing. That means it's unstable. It's called as unstable. When P is actual load is greater than the strength, then it is unstable. Neutral means when they are equal. So when it just starts buckling, it is called as neutral equilibrium. Neutral equilibrium means P is equal to PCR. Actual load acting on the column equal to crippling load on the column, then it is called as neutral equilibrium. So this is what I wanted to explain today. Now tomorrow I will be taking the derivation part. So Euler's equation derivation is there. There are 4 derivations in this because I have told you that there are 4 boundary conditions. So both ends hinged, both ends fixed, one end fixed, one end hinged, and one end fixed, one end free. So there are 4 derivations are there. Then we have to go to problems, some problems on that. Then you have one more formula called Rankine's formula. So Euler's formula and Rankine's formula. So they are the 2 important formula which we are going to use in the column chapter. Okay. So problems and Rankine's formula. So these things you have to study in columns. So today I explained you about what is a column. So column is nothing but a compression member of a building frame, or compression member of a truss is called as a strut. Then we defined the different types, classified the columns based on 2 criteria. One is based on the value of L by D, actual length of the column divided by least lateral dimension. Value less than 8 means it is short column. Between 8 and 30, medium or intermediate column. More than 30, long column. Then based on slenderness ratio value, the slenderness ratio means it is the ratio of effective length, not actual length. It is effective length to minimum radius of gyration, where radius of gyration is defined as square root of moment of inertia divided by area, cross-section area of the column. So based on the value of slenderness ratio, if it is less than 32, short column, between 32 to 120, intermediate or medium column, more than 120, long column. That is 2 types of classification of columns. One based on L by D ratio, another based on slenderness ratio value. Then we discussed about failure of columns, how it fails. So whether in the case of short column, it fails by crushing. In the case of long column, it fails by buckling or crippling. In the case of intermediate or medium column, it can either fail by crushing or it can fail by buckling. So those things we discussed. Then we discussed about the boundary conditions. So our end conditions. End conditions are boundary conditions. So in fixed end, both slope and deflections, they are 0. At the hinge is there, but deflection is 0. At free end, slope is not 0, deflection is also not 0. So these are the boundary conditions we have to know about in the case of columns, similar to beams. There is no change in that. Then coming to equilibrium of columns, stable, unstable, and neutral. So stable means actual load acting on the column is less than column strength. That is called as the crippling load. Unstable means it's opposite. Actual load is more than crippling load. And neutral means they are equal. So these are the things we discussed today about the basic definitions and these things. So this notes already I have sent you in the WhatsApp group, and also today I have sent it by mail. So please download it. And in that book, R.K. Bansal book also, that column chapter is there. Soft copy of that book I have sent already. you can go through that also. Slight difference may be there in the values of that slenderness ratio and L by D. Of course, it may slightly variation may be there in different books. Don't worry about that. You can concentrate on these values. L by D less than 8, more than 30, and slenderness ratio 32, less than 32, and more than 120. So those things you can keep it in mind, but you should know the definitions. So a lot of definitions are there, so you should understand those definitions. So tomorrow I am going to explain you the derivation of Euler's load or crippling load or buckling load. So they all are one, all are same. Euler's crippling load, Euler's buckling load derivation we are going to do tomorrow. There are 4 cases. Of course, I will explain for some 2 cases. Another 2, you can go through that. Notes in the notes, it is there. Then we have to take up some problems on that. Then we have to go for Rankine's formula. Second formula is, first formula is Euler's formula. Second formula is Rankine's formula. So how to derive the Rankine's formula and problems on that. If I do that, then your 5th module will be over. So these Euler's and Rankine's, they are used for long columns. Please note that those formulas are used for only long columns where buckling takes place. We are not worried about short columns. So only buckling or crippling where it takes place only in long columns. So how to calculate the load carrying capacity of long column by Euler's formula, Rankine's formula, those things only we have to discuss. So short column problems are not there, only long column problems. Only definition you should be knowing. So these things I wanted to tell you today. I hope you have done well in the test, second internals. I have not yet valued it. I have to start the valuation. Once I start, then I will come to know how much you have done. There were 5 problems given. You have to acquire speed. If you could not able to do those 5 problems, then that means you have to practice more problems to acquire speed. Because in the exam, in 3 hours, you have to solve a lot of problems. Maybe 15 problems or 12 to 15 problems you have to solve in 3 hours. So in that ratio, you have to solve 78 problems in 1.5 hours. That should be your speed. If you have not attempted all the questions, then it will be difficult. Because we cannot say that whatever problems you have attempted, all the problems you have done correctly. Even we cannot rely on that. So mistakes may be there. Only after valuation, you will be coming to know about that. So let me take the attendance. 1828.
Present, sir.
19003. 19003.
Sir.
005.
Present, sir.
6. 006.
Present, sir.
7.
Present, sir.
10.
Present, sir.
12.
Present, sir.
13.
Present, sir.
16.
Present, sir.
19.
Present, sir.
21.
Yes, sir.
This is comparatively easier chapter. Okay. So integration and all is not there in this. Substitution problems. Torsion and columns, they are relatively easier chapters. So that's what I wanted to tell. Today only 11 students have joined. I don't know why the strength is very less. Out of 30 students, 22 students, only 11 have joined, 50% attendance. Okay, we will meet tomorrow. We go through this, whatever I have explained today, definitions, everything, end conditions, everything. Tomorrow I will take up the derivation part. Okay.
Thank you, sir.